All right, so number 18 you said?
Yeah.
Mad Max's road warriors fix potholes in interstate highways. Max's road crews fill potholes using workers and shovels in a 1-to-1 correspondence. A worker with 1 shovel can fill 10 potholes a day. A worker with 2 shovels can still only fill 10 potholes a day, as 2 workers with 1 shovel. Draw the production isoquants. Was there a particular part of the parts that you wanted to go over in particular?
Sure about the drawings.
With the drawing?
Yeah.
Okay. So how are these, what's the production technology like? So we've got labor and capital, and we're mapping out the isoquants. So what do we know from the information of the problem? 1 worker, 1 shovel gives us what? Ten potholes filled, so that's our output, right? So our production is the number of holes being filled. And so if I add another person without a shovel, how many more potholes get filled? None. And if I add another shovel without adding another person, how many more get filled? None. So we can start to kind of reason out that we're going to get the perfect complements look to the isoquant. So this was at a quantity of 10. Okay? And likewise, I don't know if it was this problem or maybe cost down. If we had 2 resources that were perfect substitutes, so I could use a green shovel or a blue shovel, right? Something like that. Instead of measuring labor here, I had a green shovel and a blue shovel. And I want to put out or see how many things I can do with it. With 1 shovel, with 1 blue shovel, some BS, and 1 green shovel, I can do either one, right? And so the isoquant, in this case, to fill 10, a green shovel and a blue shovel are perfect substitutes with each other. And so the isoquants would look like that. And then our normal isoquants has this trade-off of the margin. These are perfect complements. That's why it's angled. So just like we saw with utility, we had 2 goods that were perfect complements in consumption. We got indifference curves that look like this. Now we have the same concept going on with production. I can use labor and capital in a 1-to-1 ratio, but it has to be 1-to-1. I get isoquants that look like this.
What's the iso cost? Can we drive that out?
I think that's later on in this problem. Before I get to that, though, so the normal isoquant that we see looks, let me just draw this, right? And so the more that this is curvy, the more they are complementary with each other. The more flatter an isoquant is, the better substitutes the 2 are. That comes about, remember the slope of the isoquant is the ratio of the marginal products. Okay? Which is, what do we call that? What's the fancy way? Marginal rate of technical substitution. Good. Okay? Is the slope of these isoquants. ISO costs, it looks like that's part C with this problem, right? Just judging by the answer key. If shovels rent for $5 and workers must pay 25, must be paid 25, draw several ISO cost lines. So 5 and 25, if we, I guess we could come back up here. What's the slope going to be of the ISO cost? In general, what's the slope of the ISO cost?
The wage rate over labor.
Good. Rental rate. Yep, the wage rate was the labor. So that comes about from the cost equation. Remember, we have cost equal to the wage rate times the amount of labor plus the rental rate times the amount of capital that you buy. If we rearrange this into slope-intercept form, it ends up being a line with a slope W over R. And so what were the numbers again? Wage was 25. So we have a slope of 25 over 5, or a slope of 5. And so if we go 1, 2, 3, 4, 5, and 1, it's a 5 to 1 slope. And so if we drew a bunch of them, it would start to look like this. And then if we had a given cost or a given quantity, depending on how the problem was set up, the optimal amount of labor and capital to use is where the two are tangent. Now with perfect complements, by the way, we'd be trucking out along this ray, right? On a 1-to-1. So we can go 2 and 2, we can go 3 and 3, and so we'd go until we found where that angle was hitting the whatever ISO cost would look like this. That would be the optimal solution under these conditions, because it's a 1-to-1 ratio. And so we still want to produce the most amount of product for a given cost. That would be how we'd find the solution. Or if they say, what is the cost minimizing amount to produce 10 units, then we want to shrink the cost down and minimize cost, and whatever that amount would be. Okay? Questions or comments there? Anything else on that problem? Okay, other problems from this sheet? I think we've kind of hit most of the hot buttons from last time to this time. I want to take a look at this next handout here, which is still in this chapter. So you guys have already worked on problems like this, but I want to kind of hit on returns to scale, which we didn't talk about. So let's what's that?
Did you say we already had one?
Did you have that one? I wasn't sure, so I printed them off again. You had it in there? Okay. Did we work through the first problem? Well, yeah, I think I later marked it. The 100 workers, I see you got something written on there. Okay. But on the, we didn't get to the, if you flip it over, we didn't do that one, right? Yeah. That's the one I wanted to just finish up this chapter with. For each of the following production functions, determine whether they exhibit constant, decreasing, or increasing returns to scale. So, remember what that is. So returns to scale dealt with the production function. And in general, we have output as some function of labor and capital. Now, in the short run, what's the distinction between the short run and the long run?
Long run, everything's fixed.
Try again.
Short run.
In the short run, and in the long run, if you want to restate your problem a little bit better. Everything's not fixed. Good. So in the long run, you have the opportunity to vary everything. So in the long run, everything's variable. So that's kind of the first important note here, is in the long run, all inputs are variable. And so by definition, in the short run, note number 2 here, in the short run, at least one resource is fixed. Now, typically, we think of capital being the fixed one, right? I mean, labor is adjustable, capital is harder to change. But our pure definition would be at least one resource is fixed. But in the long run, we can vary everything. Okay, so returns, increasing, decreasing, or constant returns are exhibited here through what happens to output if we change everything. So returns returns to scale is a long-run concept. Returns to scale, which I'll call kind of RTS, is a long-run concept. So if we double all inputs, and we observe that output doubles, and that leads to double output. What's that?
Does that make the return scale to 1?
No. We're doubling inputs, and if we double output, then we say that that is constant returns to scale. Constant returns to scale. So imagine you're running a business, you've got a McDonald's, and you take all your resources and double them. New building, new fryers, new coolers, new hamburger patties, new buns, just double everything, right? Just make a replicated store. What is the amount of output that I can get out of the store? This says if you double everything, you double your output. That's not necessarily the case. So it's possible that we could double all of our inputs and it leads to less than double output, less than double Q. That means you're experiencing decreasing returns to scale. Seems like kind of an unusual case, but what companies might face is as they double things There might be management constraints that come into play. There might be some issues that they can't be as efficient as they were before. So kind of the law of diminishing product from a management constraint can kick in. And then finally, if we double all inputs and it leads to more than double quantity, we've got increasing returns to scale. Okay, so tying this back to this problem, now look at the production function on A. So now what we're going to try to do is see what these production functions kick out if we double everything. So an easy way to look at this is to take labor and capital and make them 1. Kind of a neat little easy trick here. So if we make K and L 1 in the first production function, what is the amount of output that we produce? 17. So output equals 17 with, so for part A, if L equals K equals 1, then output equals 17. What if we double everything? L equals K equals 2. What happens to quantity? It goes up to what? 34. So what does it follow? Constant. Okay, we doubled everything, we got double output. What about B? The production function's a little goofy here. It's one of those min functions. Again, let L equal K equal 1. What does output equal to? Who's comfortable with that production function? Quantity equals the min of 3K or 4L. So how much output do we get? So let L and K equal 1, and that notation means the quantity that's being produced is going to be the minimum of 3 times K or 4 times L. So output. Yeah. Especially during lecture, we're test. So now, what if we let both of these double? What does quantity equal? 6. So again, we get constant returns to scale. All right, last one. We were dealing with quite a bit. So the production function is 15 K to the half power and L to the 0.4 power. So you might need to get out your calculators. Again, start with L equals K equals 1, quantity equals 1 to any power is what it is. L equals 2. If we double everything, quantity equals, now you have to get your calculator going. $28 is pretty close. Yeah, 27. does this production function exhibit? Okay, so 15 should have went up to 30 if so that production. All right, so here's one thing that I wanted to point out from this exercise. You may have seen this. What has this and this likely been sometimes? Have you noticed? Yeah, sometimes they were negative. Not so much on the production function side, but on the marginal product side, we get them negative. Sometimes this would be a half, this would be a half, or this would be 6, and this would be 4. So I want to do one more, and I want to raise this to the 6th power. So calculate what the quantities, we know that this would still be true at 15, but if I raise that to the 0.6 power, what does quantity equal? All right, so this might be something you haven't seen yet. I think he somewhere. But if the two exponents sum to 1, whether this is 0.7 and this is 0.3, this is 2, this is 0.9, this is 0.1, if those two exponents sum to 1, the production function exhibits constant returns to scale. And if the exponents sum to less than 1, we get decreasing returns to scale. And if the sum of the exponents are greater than 1, then we get increasing returns to scale. So this is known as a Cobb-Douglas production function. Isn't that somewhere in the text, the Cobb-Douglas? So that's kind of a specialized form that we see. Yeah?
So you said if the exponents had to be greater than 1, then it's an increasing return?
Yes.
So for C, we have 0.5 and 0.4, we get increasing return. That's less than 1.
We got decreasing returns.
Oh, okay.
Did you put the wrong thing? Maybe I heard you wrong.
Sorry.
I thought you said decreasing. So yeah. Okay. All right.
So it's greater than double.
Yeah. So now you'll start to see that, and we saw this in the utility functions too. That's just kind of a normal one to pick up on. All right. Chapter 7. We're going to start putting dollars into things, more so than the iso cost, iso quant.
So we only did this one worksheet for chapter 6.
What's that?
We only did this one worksheet for chapter 6.
No, we did the other problems early on, I think. The very first one, when we opened up chapter 6, we did this one. Pizzas and production functions. We did that schedule of numbers. I think we did one other one. You find it? Okay. All right, so let's just dig right into this first problem. The chapter is bringing in cost and accounting cost, economic profit, and really our profit maximization problem, kind of tying things together. So it's very much related, but we'll be looking at fixed cost and variable cost and what the heck happened here? Okay, not sure what went on. So let's look at the first problem with a Cookies Catering. So we got Cookies Catering is owned by Daniel Cook for the past year. It's had the following costs. So we got Dan, the owner there, $60,000, employees' salaries, electricity and water, $15,000. So Dan has always had the option of closing his catering business and renting out his building for $100,000 since he's the owner of the building. In addition, Dan currently has job offers from other catering companies offering a salary of $45,000 per year and a high-end restaurant at a salary of $75,000 per year. Dan can only work one job at any time. So, accounting profit, economic cost, economic profit. So let's just talk this one through. What is the profit equation? What is the profit equation? Good. Total revenue minus total cost. Gotta have that one down. And so now we've got a bunch of different costs here that we're trying to determine where they all belong. But it all starts here with profit equals total revenue minus total cost. And we've got the revenues of how much? 500. And then we've got these costs. So if we're looking at accounting cost, i.e. maybe what we can turn into the IRS, those expenses, what do we got from this list? Okay, electric and water at 15,000. What else? Supplies, that definitely counts, 150,000. Employee salaries, that should count. Dan's salary, that should be okay, right? He can pay himself a salary, that's fine. And if we add these all up, we get $275,000 worth of cost. So 500 minus the 275 would give us our accounting profit. Now, part B, what about economic cost?
So the accounting cost is what, 275?
Yeah, the accounting cost is 275. So these are all the accounting cost. Is economic cost higher or lower than accounting cost? Lower? Why? So if it,
Not adding every single cost.
okay,
Is economic cost taking into account opportunity costs?
yes, implicit cost potentially. And does it take into account, I guess to feed off of Blake's comment, do we ignore some accounting costs when we do economic cost? So we've got this idea that we want to take in opportunity cost is one of the top 3 concepts of Econ. So opportunity cost, do we ignore accounting cost when we think about opportunity cost? Did Dan, if he didn't spend $50,000 on, what was this, labor? Employees' salaries, what other opportunities did he not get to take advantage of?
The other job.
What's the dollar value of other opportunities that he missed out on by paying $50,000 here? What's the dollar value of other opportunities he missed out on by spending money on this particular line item?
Another salary? Oh, the renting out of the building.
No, and I'm asking an easier question and it's not really flowing very good here.
Zero.
I guess what I'm trying to say is, if he spent $50,000 here, he could have spent $50,000 somewhere else, right? So part of his opportunities are the explicit costs. Explicit costs have easy dollar signs to them. These are really all of our accounting costs. the point is that $275,000 of his expenses were easy to see, and he could have spent them somewhere else. Now, the part that makes economics is that we go beyond what the accountant had on their books and also include implicit costs. And those are the ones that we start to think, well, what could he have done if he didn't do what he did? And it might not have an easy dollar value always, but sometimes it does. And so now we start to add in the things that he could have done with his time had he not done what he did. Okay, so what else does he got? Yeah, so we're kind of on B.
This is where the job offer is $20,000 right now.
Okay, so he could have rented it out for $100,000. So that's definitely an implicit cost, right? There's no rent number. He's not paying himself rent. So he could be paying. That would be cost, which is possible if he had two different entities or he didn't have it. Basically, he has the. I would assume what's going on here is he's got the. So then there's no rent, which sounds great, except for maybe when we're trying to evaluate how well he's actually doing with this business. Now, what about the next one with the pay? What's the in there? So you want to think about missed opportunities. What's that, Adam?
I have a question.
Okay.
About, looking at his revenues or his salary when he $1,000.
Yeah. Yeah.
Given that he's the owner of the building, couldn't he, with $225,000 basically left over for your profit, couldn't he give himself a higher raise?
Possibly. I guess we don't know exactly where this comes from. We know what he's chosen to pay himself out of the business. So down here, we want to kind of reconcile that, is what we're looking to do. And possibly, is that the right number or not? What other opportunities does he have? Okay, and how much? Okay, he's got the 45. Okay, so which one do you think we should use? Did you say both? Can we do both? Let's start there. So if we add 5 plus 45,
We can't do both because we
can only have one job. So we can. It's the so our generic definition that I like to use for opportunity costs is the highest valued alternative foregone. It's the thing you gave up. It's the thing you would have done if you didn't do what you were doing. But it's the highest valued alternative, which means we should be using which one? The 75. Now, can we use the whole 75? Would it be appropriate to use the whole 75? No. Because why? He's paying himself 60 already. So what he's really missing out on is the extra 15. And now we've got his full opportunity cost calculated because he's paying himself 60 and he's got 15 that he's missing out on. All right, so after we
economic cost of $115,000.
115 plus accounting cost of 275. So you got to add the monetary and the non-monetary cost of the business. Add those two things together, you should get 390. So profit equals 500 equals 110. Up here, he was making 225,000. 500 minus 275. So on the books, when you looked at his business, you're like, oh, you're doing pretty good. You're doing 225. How that shouldn't be doing. If revenues fell to 400, if revenue, and we wiped out 100 out of this, then he's really only making 125. But down here, he'd still be up 10, which is good. If we knock down to 350, revenues fall to 75,000. But down here, if we knock off another 50, they fall to a negative 40,000. Now this is where the power of using opportunity cost comes into play, especially because a lot of business owners might fool themselves into thinking they're doing okay by making 75,000, right? And in fact, he might even be saying to himself, well, I'm making 75 and that's the same that I could be doing at the high-end restaurant, so I'm okay. Follow what I mean? He's not maybe going to make the right decision if he's including the implicit cost. The big one here is the building. If he includes the fact that he could rent out his building that he owns, he'd realize that he's actually losing 40,000 and then flip. Go work for the high-end restaurant, make 75. Rent the building out, get the 100, 175. And even if we take away the 60,000 that he was paying before, we're still back up to $115,000 worth of profit, which was exactly this number here. Okay? Boy, I wouldn't want to rewrite. Hopefully you guys went through the chain and as you think about that. I mean, this is definitely principles class stuff. I mean, we did this in class before, but it's good to
So the operating
work through it
profit
again.
for this one is 110,000, right?
Right. The economic profit on the first go round,
110.
110, I think. Yeah. 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 The actual answer of what the question was asking, we kind of dug a little deeper. Okay. On the next one, I'm going to kind of skip a little bit, but go ahead and read the problem. So we've got Fields Forever is a small farm that grows strawberries to sell local farmers. It produces strawberries using 5 acres of land that it rents for $200 per week. Fields Forever also hires labor priced at $250 per worker. The table below shows how the output of strawberries measured in truckloads varies with the number of workers hired. So look at that list, tell me about it, and talk to me. What does that list mean? What are some of the properties that you see about the list? Okay, oh, I must have shut it off. Just trying to turn on the light. What's going on with those numbers?
Basically, after one labor worker, we have an increases per
Okay.
4.
All right. So what's it exhibiting? What would you say it's?
Increasing marginal cost.
There. That's what I wanted was the lamp. Let's see how that looks. There we go. Okay, increasing marginal cost, right? Because cost we can get at the same amount. As we look at the labor, we add 2 workers, we get a doubling here of the amount of strawberries. So it's going up by 1 crate, but now it takes 4 workers to add another crate. This is a little weird than what we've done before, right? A lot of times I've given you guys problems of 0, 1, 2, 3, 4, 5, and then I put the diminishing product here. We go up by 10, and then this goes from 10 to 17, 17 to 21, 21 to 22 or something. And so you see the diminishing marginal product that way. So this table's getting that same concept, but we're showing labor at kind of different rates, and then it's going 1, 2, 3, 4, 5. So it's still exhibiting diminishing marginal product. All right, so what is fixed cost? What is fixed from this problem? Rent. So we got produces strawberries using 5 acres of land that it rents for $200 a week. So that's a fixed cost. And what's our variable cost? Yes, but it's not the wage rate. So what our variable cost is our labor cost tied into the wage rate, but the wage rate's fixed. And so our labor cost is the variable cost, right? And that's just shown here by the production function. In order to get more strawberries, I need more workers. That then ties into kind of what we saw in principles class of this type of answer, which you don't have to scribble down. This is in your book, by the way, too. I just wanted to kind of get your juices flowing before we jump into the formula part of this. So, again, somewhat of a principles review here. We've got the labor column, the output column, the fixed cost, 200, 200, 200, 200, right? Going fixed all the way down no matter how much strawberries we have. The variable cost, so how much our labor cost is. You can see it going from, to produce 1, 2, 3, 4 strawberries, we got 250, 750, and it's going up. Total cost is equal to variable plus fixed, so that's the total cost of our operation. Notice that that's different than what we just did here with implicit, explicit cost. It's just the other thing of separating cost into those that vary with quantity and those that don't. That's it. So all costs kind of can be thrown into this category or this category. They either change with output or they're fixed with output. And so then finally, the granddaddy of them all is the marginal cost, the incremental amount of cost for an additional unit. And we see that the cost of the 4th strawberry, the 4th was $1,250. The cost of the 2nd load of strawberries was only $500. And you're like, what's up, man? That doesn't make any sense, right? If we're thinking about the cost of strawberries, I go to the store and they cost what they cost and it seems fixed. That all comes through to us through the law of diminishing marginal product. Each additional worker is not as productive as the previous ones. So that concept, the law of diminishing marginal product, drives the result of the law of increasing cost at the margin. Marginal cost curve is upward sloping and J-shaped. All right. Questions or comments on that little hash out from days gone by? I know that's right off the top of most of your guys' heads, so it's probably just a waste of my time to even go through that. So, since you guys got these notes all in one place, let's add some more notes for this stuff. This will look familiar to you guys from principles class again. But burn this into your memories if you don't have it burned in already. So total cost is equal to the sum of total variable and total fixed cost. We will quickly start talking about average costs. So if we were producing 5 truckloads of strawberries, how would I find the average total cost? The amount of not workers. You could do workers and get a different number, but if I'm looking at the average total cost of strawberries, I'm in the strawberry business, right? I make strawberries, which is a function of labor and capital. And so I want to say, well, what's the average cost of producing this 4 truckloads of strawberries? I know that my total cost is $100,000 because I added 60 plus 40. How do I find the average cost per truckload of strawberries? You're on to something that we're going to get later, but just talk to me in terms of total cost. If I have $100,000 of total cost, and I produced 4 truckloads of strawberries, what is my average cost per truckload of strawberries? $25,000. What did you do? Good. What I do to one side of the equation, I got to do to the other side of the equation. And then I learned that the average total cost of doing business is equal to the sum of the average variable cost, which is what Blake was kind of jumping to, plus the average fixed cost. Have this box committed to memory, burned deep. Now, marginal cost, the granddaddy of them all, isn't up here at all. You've got about 5 formulas that are all embodied into this thing. If I asked you, what's the average variable cost formula? Now you know it. The average fixed cost, average total cost, the sum of the totals, the sum of the averages. But the granddaddy is missing. The granddaddy is the change in total cost divided by the change in quantity, which looks awfully close to this one, but very different, right? The change in total cost divided by the change in quantity. Now, to play the math out a little bit more, we could look at the change in total variable cost over the change in quantity plus the change in total fixed cost over the change in quantity. But how do total fixed costs change in the short run? How much do they change by? Total fixed costs.
0.
They're 0. So this is garbage. It's actually equal to 0. Now you've got 2 formulas here that you need to know for marginal cost. Change in total cost, or the only things that are going to change anyway are the variable costs. So it's the change in total variable cost or the change in quantity. All right, so those are the formulas, kind of the key ones to have to memory.
Max, I think point is where the average total cost across the marginal cost, right?
Where the total, and add that in. Let's just give you the here's the standard graph. This is as good a time as any to do it. You guys might remember this. Make this one so that it's narrowing down. Look at how I did that. So there's a big minimum point for the average total, minimum point for the average variable. Just make sure these are squeezing down together. And then the marginal cost curve can be J-shaped, and it cuts by definition. All So we will do for Wednesday the chapter 7 learning curve, and so Wednesday we'll still have Monday, but if you want to get a jump on things over the weekend, learning curve and the short answer problems in the back. Adam, did you end up finding out if as far as knowing which ones are the starred problems, or did you do it by the way I said that last email about whatever ones are in back are the ones that are starred?
Yeah, there's only there's only 6 of them that actually have the solution.
That's right.
Online.
That's what they are. It's always 6 of them too. So yeah, you can always backdoor it. Yeah.
Oh, both.
Yeah, we're going to do some more in class, but if you wanted to get an early jump like on the learning curves or something, you'd feel free to.